Okay, we'll go ahead and get started since it looks like that's it. And then what we'll do, we'll put a quiz up. And so for all those people who decided not to show. So how was it last week, Jessica?
I had more students than just Mauricio and Alberto.
Okay.
But that's so weird because it's usually the evening is Michaela and then her sister.
Yep.
And I think there's another student.
Taylor.
Yes, her. Did she go to like your morning session
Nope.
or did any?
Oh, nope, none of them. There we go.
There we go. There's more.
I was just getting too anxious. I didn't wait it long enough.
Be patient then, Doctor. Let's be patient.
Come on now. Patience is overrated. Ha, humbug.
No. With patience comes great things.
Okay, so let's go ahead and get started. So we'll do business first. We're gonna have a short lecture because we have a short lecture this morning. It's gonna be about an hour, and you guys are gonna have a simulation. The simulation isn't up and running yet. Everything that I've done this weekend basically wasn't saved, so it has to be redone. I'm in the process of redoing some of the things that I've done this weekend. So hopefully by the end of tonight, I'll have it up and running. Me and Candace had a little bit of a fight, so we'll have it all up and running tonight, so before I go to bed. So you guys will have a simulation that is going to be due by the end of the week. And then on Wednesday, you guys are going to have a lab. So you guys are going to need, I'll tell you what you need in advance. You're going to need your diffraction slide. You guys have your diffraction slide. And that reminds me, Jessica, I have to drop off papers for you. Where's my other stuff? You need your black paper. Hold on 1 second. I lost my kit. Okay, I'm going to use your black cardstock. You're going to need to use your cutout for your spectroscopy. So you're going to use this with your black cardstock. The black cardstock is what you're going to use for the spectroscopy, for the actual building it. And then this is going to be the lens that you're going to be using. Okay. Give me a thumbs up if you guys agree. So you guys will have the glow sticks. You should have one that is opened already. You should have one that is 3 different colors. So you're going to use those 6 all together. You're going to use your LEDs. You're going to need your alligator clips. I don't know what I get my alligator clips. Your battery and your battery cap. You need to connect these to alligator clips. So you may want to start doing that right now. So if you guys have your alligator clips available. Yeah. No? And if you don't have any of these things, let me know as soon as possible. I'll be traveling up and down the valley this week. So I'll be able to hand deliver it to you if you're missing anything. So Jessica, tell Selena I'll hand deliver hers. Okay. Questions, concerns, Cash?
Dr. Henry, I have a question.
Yes,
So you will be posting the lab information on Canvas, right? Still.
that is correct. I will be posting it on Canvas. I've had some trouble. It's technically was already posted, but I have to redo it again because I've had trouble with saving my everything that I was putting onto Canvas.
Oh, okay. Thank you.
Okay, so it'll be done. It'll take me probably tonight, tomorrow, get it all up and running.
So the lab will be on Wednesday?
Yeah, so you'll have a simulation, and that's going to be the first thing that you have to do. So try to get it done before Friday, your simulation, and then your lab will be done on Wednesday. You guys will be doing, we'll be doing a lab together on Wednesday.
Okay.
So that'll be our first lab, our first hands-on one. And then we also need to start talking about when we're going to meet for the real other lab. Okay. You guys with me so far?
Yeah.
Perfect. Okay.
Yes.
Okay. So let's go ahead and get started. So I know Jessica went over electron configuration with you guys. You guys are feeling comfortable about it? Yeah, no, maybe?
I hope
Yeah, it's
so.
not too bad.
Okay. Let me see. Do you feel confident, Jessica, in their confidence?
Yes, I will. Yes, let's be optimistic.
Okay. Okay. Speak now or forever hold your peace because we're going to be moving. Okay. So you guys have done electron configuration, but before you guys get really knee deep into electron configuration, let's talk about your quantum numbers. So there are 4 quantum numbers that you're going to be focusing on. Okay. So the thing about quantum is relying on the quantization of ions, right? So basically we're looking at discrete energy levels, the discrepancies between each of the different electrons that are in an atom, okay? And also the fact that electrons can jump from one energy level to another. And so that is the premises of the quantum theory, okay? So now, as I said, there are 4 quantum numbers. Your very first quantum number is called your principal quantum number. That value goes from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It can go on forever, essentially, right? So this first quantum number represents the energy level of the ground state of that electron, okay? So it's considered that very first where that electron is at ground state. So you guys are familiar with the periods on the periodic table, right? Thumbs up if you understand that period.
Yes.
Good. Okay, good. Okay, so the periods represents those energy levels. So down the side of the periodic table, that's letting us know the energy level, right? So 1 represents that first energy level, 1. That, okay. 2 represents 2 represents, you know, the second energy level. 3 represents the third energy level, so on and so forth, right? If you notice on the periodic table, pull up my periodic table. Can you guys see my periodic table? 1, 2, 3, 4, 5, 6, 7. It goes up to 7, right? So, but what did I just say? Did I say that it stops at 7? Yes or no? Thumbs down if it's a no, thumbs up if it's a yes. Do I have thumbs down? Am I making stuff up? See, we need a thumbs down. Okay, so crying if it's a no, or joy is what they call it. Okay, good. Okay, so I have one person that responded. Graciela, are you there? Are you playing with your chickens?
Oh no, I'm over here and paying attention.
Okay, I'm just checking because you're not responding. You're not giving me a thumbs up or a thumbs down, so or a cry, you know. So I'm assuming.
Oh,
that-
sorry, it's because my mom came in, so she was asking me something, but I'm still paying attention.
Okay. Okay. So that basically means that we can go to higher energy levels, right? Because you guys got to understand, science is dynamic. Science is constantly changing, right? We're learning more and more every day about different elements and things like that that we're actually looking at, right? So initially, when I was in school, you know, back in the Stone Age and stuff like that, the periodic table only went up to radium, right? And then all of a sudden we started getting uranium. Oh, that isn't true. There's uranium and all those guys. But in theory, there was a limit to what the periodic table went up to, right? But now we have more and more elements that are starting to be found and discovered. And there's going to be a point where we're going to get to the 8th energy level, and then possibly the 9th energy level. Okay? Are you guys with me so far? So the way the
Yes.
periodic table is designed is so that we can incorporate those guys later on without any problems. Okay? Let's see. So first quantum number is called what again? Type it in the chat. Type it in the chat. If you're not going to talk, type it in the chat. We'll get those typing skills up and running. Anyone? First quantum number is called what?
Mauricio typed in principal quantum number.
Thank you, thank you. Why isn't my chat showing? Okay. Now Zoom ain't working for me. Okay, so as we recall, right? So here's the nucleus. This represents that first energy level that you'd find that an electron in. Okay, that would be the second energy level. That would be the third energy level that these electrons can be found in. Okay, so that's going to be very important. It represents those energy level. Again, that is called our principal quantum number. Piece of cake so far?
Getting there.
Getting there. Okay, working on it. We'll get it there. Okay, so the next quantum number is going to be the angular momentum quantum number, right? So this actually tells us, it helps us define what we call the orbits. The orbits that are going to be, it's going to be characterizing one of the characterizations of the orbit of the electrons, okay? So when we're talking about atomic orbits, we're making reference to where those electrons are most probably at, you know, the region that they're most probably at, okay? And it's really important to understand that this is a three-dimensional type of structure, okay? And I'll show you what the orbits are going to be looking like. Okay, so I said the next quantum number is called the angular momentum quantum number. That is our second quantum number. Now, the angular momentum quantum number, we define it as L. L can go from 0 to n minus 1. So if n is 1, how big can L be?
0.
Okay, L can only be 0. If n equals 2, L can be what?
1.
It can be 0 or it can be 1. Okay, so it goes up to n minus 1. Okay, if L is 7, if n is 7, what is L?
Zero, 2, 6.
So it's 0. Is it 0, 2, 6?
No,
Oh, 0, 2.
0 through
I did
6.
it. 0, 2, 6. So it'd be 0, 1, 2, 3, 4. Sometimes I'm special. 5 and 6. Okay, so that's what you're saying. 0, the word 2, 6. Okay, piece of cake. Okay, so let's talk about what L actually means. Okay, L represents our subshell, okay? Often we will exchange that term orbital. You'll see orbital a lot of times. Now, that isn't necessarily true. It's really called a subshell because within that subshell, you have orbitals, okay? And so often we'll exchange them, and it's not really accurate when we use orbitals, but we will do it, and you'll see it in textbooks all the time, okay? So, let me clear. Okay, so L equals 0, that's going to be the s orbital. L equal 1, that's going to be the p orbital. L equal 2, that's going to be the d orbital. L equals 3, that's going to be the f orbital. After that, because we went up to 6, right? When we said L is when n is 6, n is 7, we went up to 6. So L equals 4, that's going to be the g orbital. L equals 5, that's going to be the h orbital. And L equals 6 is going to be what? Anyone? Anyone? Anyone?
Mauricio
That
said.
is right. The I orbital. Because, as I said, science is dynamic. It's going to be changing. You guys are going to start discovering some of these other elements at some point, right? And so we're going to get to the point where we're going to actually have the I orbital, right? Someday. Okay? Questions, concerns, cash. Okay, good. So the first quantum number is called what again?
The principal quantum number.
Okay, and it's represented by what letter?
N.
Okay. Okay, so we've talked about the angular momentum quantum number, which is our second one, right? We know that that represents our subshells. So let's actually talk about the specific orbit. So when we talk about radial nodes, remember when we talked about nodes where those points where they're clipping together? You guys remember that? Like if you were talking about a wave, the points where it clipped? Yeah, no, maybe? No. Okay, at least you're honest. Okay, so you guys don't remember very back in the very beginning of this lecture, we were sitting there talking about have a wave, a finite wave, right? So, and then if that wave was going the opposite direction, this here would be nodes. That would be one node, that would be two nodes, that would be three nodes, that would be four nodes. Okay, so it's kind of like that 0 point, or where the wave is kind of caught together. You guys remember that?
Oh yeah, I remember that now.
Okay, so those are going to be like your radial nodes, right? But instead of doing just a regular wave, we're doing, waves like this, right? So when we talk about that, come on, we can calculate the number of radial nodes, right? And so the way that we would calculate the number of radial nodes is we'd go n minus L minus 1. Okay, n minus L minus 1 is going to give us the radial node. So if we're talking about the first energy level with a 1s, so 1s, so what is n in the case of the 1s? N is equal to what? Anyone? Anyone?
1.
1, right? Because this here represents the energy level that we're on. This here represents the angular momentum. So what would be the angular momentum? What is L in this case?
0.
0. Okay, so then we have 1 minus 0 minus 1 equals 0. So in that case, there are no nodes. Okay? If we have a 2s, then n is equal to 2, right? 2. It's also on the board. Come on now. So S, again, is what? The L in the case of the S is going to be what?
0.
0. So in that case, we have 2 minus 0 minus 1. So if I had 2p, what would be the N? And what would be the L?
The N would be 2.
And the L would be
1.
okay. So then how many nodes would we have? How many nodes would that be? How many?
0.
We'd have 0 nodes. So are you getting it so far?
Yeah.
Okay, so what do those nodes actually look like in the case of the s orbital, right? So we're taking a look at the different s orbitals, the 1s, the 2s, 3s, right? So let's take a look. Okay, here, this guy, the guy in the blue, this is 1s, right? It has no nodes, meaning that it has no gaps between the next thing that's there because there's nothing there. So no nodes. Where the 2s, ooh, my error is almost perfect, right? There's a gap here, there's a gap here, right? Right? So, but that overall represents a single gap. So that's 1. So that would have 1 node. This guy has 2 nodes. That's 1. And here's your second one. Do you guys get that? So it's representing those gaps between the S subshells, the 1s, the 2s, and the 3s. Is that clear? Good. Okay, so now that we talked about that, if you guys notice, the S has a particular shape associated with it. It's considered to be spherical. Now, what about the P? Well, let's talk about that. On now, clear. Okay, so the P subshell has a spherical shape. I'm sorry, the S subshell has a spherical shape. The P subshell has a dumbbell shape. So it looks like, have you guys seen budding yeast before under the microscope? Looks like that. Okay. And the F, the D and the F, they're a lot more complex. Okay. So these shapes are going to represent the orbits that the electrons are going to be going. Okay. So it's the 3-dimensional regions that the electrons are. Okay. So come on now. The 1s, or just the S, right? Spherical, right? Just a sphere, round. The P, each of those are dumbbells. Now, you guys remember, I know Jessica talked about this. We'll see how much you guys remember. How many electrons can the S subshell hold? Anyone? Anyone?
Hey, what was the question again?
How many electrons can the S subshell hold?
2.
2. That's right. It holds 2. How many orbitals does the S subshell have? Anyone?
Yeah, I don't know that one.
1. It's a sphere. That's it. That's the one. So that sphere basically can hold 2 electrons in it. Okay. So, but it has 1 orbital because that's the sphere that it makes. Where the P has 1, 2, 3 orbitals. Okay. It has what we call the PX, the one that's on the x-axis. We have the PY, the one that's on the y-axis, and we have the PZ. Oops, sorry. PZ, and then the PY, the one on the y-axis. Okay. We also call it P minus 1, P0, and P1. Now, this here also represents another set of quantum numbers. We call these quantum numbers, it's the magnetic quantum.
For testing purposes, would we have to know how like the atom is gonna look?
Of course. Well, you mean, is it how the atom is going to look, or is it the electron?
Or the electrons?
Yeah. So you're going to need to know where that electron is. Yes. So for testing purposes, you do need to know the shape of the different orbitals, right? So you want to familiarize yourself with the shapes of the different orbitals. At least be able to identify, right, visually. Okay. Does that answer your question, Jessica, for testing purposes?
Yes, it does.
Okay. So we call this, the symbol for that is called ML. Okay. ML is the magnetic quantum number. Now, this represents each of the different orbitals. So for instance, the ML for the s orbital, or the s subshell, is going to be equal to 0. The ML for the p subshell is going to be equal to L minus L in general. We'll say in general should be minus L to L. Okay. So we know for the s orbital, L is equal to what? Or s subshell, L is equal to what?
0.
0, right? So then in that case, you only have one possibility. For the p subshell, P, L is equal to what?
1.
1. So in that case, we can go from ML is going to equal minus 1, 0, or 1. Minus 1, 0, or 1. Okay, 1, 2, 3. 1, 2, 3. Okay, so for the F subshell, L is going to equal what?
2.
L is going to equal 2.
Oh, wait, for the
So-
F orbital?
Yeah, or is it 3?
It's 3, yeah.
So L is going to equal 3. Yeah, I skipped D. Okay, so then ML is going to be, what can ML be?
Does it go from -3 to +3?
That's right. So it'll go from -3 to +3. So that's -3, -2, -1, 0, 1, 2, 3. Piece of cake? So how many orbitals does the F subshell have? One, two, three, four, five, six, seven. F negative 3, that's 1. F negative 2, that's 2. F negative 1, that's 3. F0, that's 4. F1, that's 5. F2, that's 6. F3, that's 7. Make sense?
Yeah.
How many electrons can the F orbital hold?
8.
Just 8. 2 here, 2 here, 2 here,
14.
2 here, 14. That's right. Okay, piece of cake. Okay, so now we have 3 quantum numbers. So now, let me take a step back. What in the hell are these quantum numbers for? Anyone?
Do they help identify each element?
Not each element, but each electron in an atom or in an element, you know? Okay, so they identify
Okay.
each electron. So each electron in an atom has a specific address. Okay, do you live with Alberto?
Do what?
Do you live with Alberto?
No.
No. So you have a different address than Alberto. Is that true?
Yeah.
Okay. So if I sent a package for Alberto to your house, would Alberto get it? Anybody want to take a risk on that one? Would Alberto get it?
No.
No, he won't get it because
No.
it's going to Taylor's house. Okay, so Taylor has a specific address. Alberto has another address. So each and every electron in an atom has a specific set of quantum numbers that are kind of like the address, right? What is your neighbor's name, Angela?
Me?
Yep.
I can't remember.
She's a great neighbor. Okay, we'll call him Ted. So Ted lives next door to Angela, right? So Ted has a specific address than Angela. They are on the same street, right? So they could be the same principal, but they have a different address. So they have to be different from each other, right?
Yeah, especially since I live in apartments. So it's technically the same address, but we have different apartment numbers.
That makes them different, right? Okay, so quantum numbers are like that. So every electron in an atom has a unique set of 4 quantum numbers. We've talked about 3 of the quantum numbers. Let's talk about the last. Then we'll do a recap. Oh, wait, before we go. Okay, so for magnetic quantum numbers, or if we won't say magnetic, for the angular momentum quantum number, L equals 4, that would represent what? Which subshell would that represent? That's right, it would be the G. How many electrons or how many orbitals can we have in the G? right, 9. So there'll be 9 G orbitals for L4. Okay, so you guys see how that works? So then what would it be for H? Look at the trend.
11.
That's right. Piece of cake? Good?
Kinda.
Okay. Okay, so let's see. So the other thing that we want to talk about is degeneracy, right? So we know that the principal numbers actually go up, right? But when we talk about degeneracy, we're also talking about that energy level, right? And so there are what we call degenerate energy levels, certain ones. So if we went, like for example, we have the 2s, the 2p, right? I mean, sorry, the 2s, the 2p. And so in that case, right, where is it? Let me get my periodic table. Come on. Oops, wrong thing. Periodic table. Okay, see it? Okay, so here, that's our 2s. This here's our 2p. This is our 3s. This is our 3p. This guy is our 4s. What is this right here?
3D.
3D. So we went from a 4s energy level to a 3D energy level. Right? So that kind of represents our degeneracy, right? And you guys are going to see this as we move into bigger orbitals, right? So we see the same thing happening when we get to the F orbital. And we'll see the same thing happening when we get to the G orbital. Are you with me?
Yeah.
Yeah. So what does that look like? Come on now. Okay, clear. Okay, so this here represents the energy scale. And you guys are going to be playing with this a little bit later. So here's our 1s, here's our 2s, here's our 2p, 3s, 3p, 3d, 4s. Now, in terms of energy, which one is higher, 3d or 4s?
3D.
3D.
Yeah. So 3d is higher in energy, right? So that's the reason why we fill up the 4s first, and then we go to the 3d. Okay, because electrons are lazy. They don't want to use up more energy. They're going to look at ways to try to keep it low. Okay, so how are you feeling so far? Good, bad, ugly?
Well, my personal opinion, I feel more lost than before.
Really?
Yes. It's because since you know the first class that I had with you, I've been always really confused with the 1s, 2s, and then go to a periodic table and go to the table and like that, you know. So I get confused in that part.
Mm.
The counting, where you go 1, 2, and then you put the number. Yes.
Okay. Well, I'm glad that we're talking about it because we need to find a way of getting you unconfused. So you need to set up some time with Jessica. If not, you need to set up some time with me during my office hours. Okay.
Yeah. Mm-hmm. Yes.
Okay. Anyone else? Alberto, are you with me?
Yes, I am.
Okay. Let's see. Good. Okay, so we've talked about 3 of the quantum numbers, right? And if we look at it, so this would be L equal, sorry, L equal, sorry, it should be L equal, it should be, sorry, this should be your -1, this is your 0, and this is your 1. Okay, so if I had an electron here, what would be my principal, what would be the first 3 quantum numbers? N would be what?
1s, 2s. Wait, what?
What would be N in this case? We're talking about the 3 because we have N, the other one is L, and then ML.
N would be 3.
N would be 3, right? Representing the energy level. The L would be,
P.
it's P, so then that means that it's
1.
okay. And the ML would be for this one electron.
I'm -1, 0, and 1.
So it could be -1, so -1. So if this electron is here, not in this one, so then it's what? This electron right here.
Oh,
This
just
electron
0?
right- Yes, so in that case, the ML is 0, okay? Now, our last quantum number is called MS, and that stands for spin, or magnetic spin, okay? The MS could either be a half, a plus a half, or it's gonna be a minus a half. A plus a half means that it's spinning in one direction, and then a minus half means upside down, spinning up at the opposite direction. Together, if they're both spinning, they should cancel each other out, so there's no energy gain from it. So you're also not developing a magnetic field. You want to prevent a magnetic field forming. So you always have in the same orbital electrons that will be going in opposite spins. So we often will draw that electron. Are you with me? Did I lose you?
A little.
Okay, so
So
don't worry.
it's just like this. MS is like the spin.
MS is like the spin, okay? So the last one is called the spin quantum number, or the magnetic spin quantum number. So MS could either be a plus a half or a minus a half, right? That's just representing this. The electron's either spinning in one direction or the other direction, right? Now, because every orbital can hold 2 electrons, when the electron is full, you have no magnetic field associated because they're going in opposite directions. They cancel each other's magnetic field. Okay, you don't have 2 electrons facing each direction. You always have them going in opposite spins. Does that make sense now?
Yeah, it does.
Okay. Clear. So that means we're going to talk about Pauli exclusion principle. Pauli exclusion principle basically says that electrons, there are no 2 electrons, no 2 electrons have the same set of 4 quantum numbers. 4 quantum numbers, what are they again? Anyone? Anyone? Anyone?
What was the question?
4 quantum numbers, what are they again?
You do want like the
names.
Hold on. The secondary, the magnetic, and then the spin.
Okay, so we got the spin, and I heard the magnetic, okay?
angular momentum.
The angular momentum. L is angular momentum. And the N, called the principle?
Principal.
Yep. Okay, so no electron in an atom will have the exact same location, right? So they'll never have the same quantum number. They're always going to be different. So in one atom, let's say we're talking about carbon, you won't have N equal 1, L equal 0, ML equals 0 plus a half MS. Okay. And have that repeated. So you will never have the exact same 4 quantum numbers for an electron. Okay. Make sense? Why is that?
Because it's like the location of where the electron is at.
It's kind of like the location where the electron is at. And we know that these first 3 could be the same, but that last one has to be changed. That means it's in the opposite spin. Okay. So you're always going to have one that's going to be opposite of the other. Or you could have one that's opposite of the other. Not always have it. Okay. Is that clear? Don't worry. On Wednesday, it'll be all cleared up when we go through it really in depth. Okay, let's see, where are we at? Okay, so we also know that you can't have more than 2 electrons in one orbital, right? 1 positive, 1 negative spin. Okay, so that's also part of Pauli's principle, Pauli's exclusion principle, right? So if we have 3 electrons within an orbital, we know that that's wrong, right? Because that disobeys 2 of Pauli's exclusion principle. 1, because that would suggest that one of those would have the exact same quantum number as another electron. It disobeys that one, and it also disobeys the fact that you can only have 2, 1 positive spin, 1 negative spin. Are you with me? Mauricio. Are you there? Yes. You understand? Yes. Alberto. Yes. Okay. Taylor.
Hello.
Are you there?
Yeah.
Do you understand?
Yes.
Okay. Okay, so our last thing, right? That we're going to talk about today, then I'll let you free. You guys are actually doing better than the other class. Let's see. So this is just basically a summary, right? So these are the summary of the 4 quantum numbers. You need to be familiar with them. You should be able to identify the electron in an atom, let's say on the periodic table or in a sheet, based upon the quantum numbers. We're going to work on that next time. Questions, concerns, Cash? Ready?
I have a question about the Labster. Is it online or is it on Canvas?
It's on Canvas. It's going to be on Canvas, but it's not up yet. I did it this weekend, and I loaded a lot of stuff up this weekend. Everything that I loaded up this weekend didn't.
Oh, okay.
So I had some issues with Canvas. It actually locked me out. So, and didn't tell me a lot.
Oh.
I was saving stuff and nothing saved. So I will be putting it back up tonight, hopefully. And if not, it'll be up tomorrow. So you guys will have till Friday to get it done.
Okay.
Okay. And it'll be about the Bohr atom. Any other questions? So there's a Black History event this week. I forgot to mention that. If you guys want extra credit, pop your bodies in at noon and watch it. It'll be roughly about an hour. And let's see, is there anybody who participated? Nobody's there. Well, if you guys talk to Selena and Abby, they represent it, you know. So give them thumbs up, let them know. Congrats, they're winners of something. So they did a good job. They did a great job with painting, and Abby did an incredible job with the poetry performance.
Oh yes, I was there. It was really nice.
Yeah.
Yes.
Okay.
Extra credit.
Yeah. So on on Thursday, there's another chance of extra credit, and it's at noon. So all you have to do is click on the link, show up, take a picture midway, and you guys are good to go. Okay, questions, concerns, Cash? Yes.
Checks, debit,
We will,
credit.
on Wednesday, we will go over the Z effect. I will actually extend the homework so you guys will be able to do that. Okay, because Z just basically stands for the atomic number. Okay. And so we'll see because the atomic number represents what again? Does anybody remember? Back from the very first semester.
It's the number of protons which defines the element.
That's right. It's the number of protons that define the element. So you want to sit there and figure out how the number of protons are going to play a part in it as well, too, right? So, okay. Questions, concerns, Cash? Okay, so we'll talk about that. And don't remind me early, Mauricio, remind me in the beginning of the class so you guys can finish that homework. Okay, I will see you guys on Wednesday.